Good morning, guys. We're going to start the second section in chapter 12. We're going to look at evaluating our limits analytically, which is basically the same thing that we were doing in part 1, but now we're not going to have the graphing calculator or a picture of the graph to be able to do the limits. So we're not going to be using tables or graphs. We're just going to be using the function and figuring out how to get the limits, which we've done for piecewise by doing the left and the right-hand side by just plugging it in. But now we're going to look at some that are a little trickier. All right. So the first thing that we want to do, so these are the steps that we're going to follow as we're doing the limits, just being given a function. So we always start with direct substitution, which means we're just going to replace x with the value that x is approaching. And the only time we have to do more is if we get an indeterminate form, which in most cases is going to be 0 over 0. So any other number you get is going to be the limit unless we get that 0 over 0. And if we get that indeterminate form, these are some of the steps that we could do. All right, so if it cannot be evaluated by direct substitution, in other words, get 0 over 0, we're going to try to divide out common factors, which basically means reduce the fraction. We can try rationalizing the numerator. We'll do an example like that, or simplifying the fraction. So if we have a complex fraction, we'll do that. And we do this so that we can simplify the function so that we eventually can do direct substitution. And then if we want, at the end, we could use the graphing calculator or a table to check our results. All right, so if we want to type the function under y1 and then set up a table around the x value and see if our answer is correct, that's what we would do. But we're not going to use the table to find the answer. We're just going to use it to help check our answer. Okay, so let's look at this first example. So this is an idea of factoring technique. So the first thing we always do is the direct substitution. So if we replace x with 4, in the numerator, we would get 4 squared. That would be 16 minus 5 times 4 is 20. 16 minus 20 is negative 4 plus 4, which would give us 0. And then if we plug 4 into the bottom, 4 squared is 16 minus 8 would give us 8 minus 8, which is also 0. So because we got 0 over 0, which is an indeterminate, not undefined, all right, a constant over 0 would be undefined. Indeterminate is 0 over 0. That means that we have to try one of our techniques. And since these are both quadratics, all right, we'd want to see if we can factor, which we can. If we factor the numerator, factors into x minus 4 times x minus 1, and the denominator factors into x minus 4 times x plus 2. So right away, we can see that there are 2 discontinuities for this function, x equals 4 and x equals negative 2. But the question is, does the limit exist at 4? All right, so at x equals 4 and x equals negative 2, we have discontinuities. If the limit exists, remember, that's a removable discontinuity. If the limit doesn't exist, then that would be a non-removable discontinuity. So right here, now that we're factored, we can cancel out the common factor, which in this case is x minus 4. That would lead us to x minus 1 over x plus 2. And now that this canceled, what happens is that gets rid of the 0 over 0 issue we were having before. And now we can do our direct substitution. We can replace x with 4 in our new function. All right, so even though we know it's a discontinuity, when we simplified the function, we got this. And when we substitute, we end up getting 3 over 6, which reduces to 1/2. So what that means graphically is that at x equals 4, this function doesn't exist. So there's a hole at the point 4 comma 1/2. So the limit exists there, even though the function doesn't. So we would say there's a removable discontinuity at x equals 4. And if we're evaluating the limit, we would say the limit equals 1/2. And now if we wanted to go back and check it on the graphing calculator, we could type our original function under y1. Make sure you put parentheses around the top and the bottom. Set up a table around x equals 4. And you should see as you approach from the left and right, it's getting closer and closer to 0.5, all right, which is 1/2. At 4, it's going to say error, all right, because again, this function doesn't exist at 4, but its limit does. Okay, so let's take a look at another technique. So for this one, again, we have another polynomial over a polynomial. If we do our direct substitution, which we always start with first, so you don't want to start with factoring, you want to start with your direct substitution. When we plug 1 into the top, we get 1 plus 1, which is 2, and we plug it into the bottom, we get 0. So right away, this is one that we wouldn't have to simplify at all. When you get a constant over 0, that's undefined, which would mean the limit does not exist. All right, so there's no need to try to simplify this one, only if you get 0 over 0. What that means is that at x equals 1, this function has a non-removable discontinuity. all right, which would be a vertical asymptote in our case, since this is a rational function, because the function doesn't exist and the limit doesn't exist. So that one was pretty quick. Let's try another one. So for this one, rationalizing, we're going to do the limit as x goes to 0 of this function. And again, if you're following along, feel free to pause the video and kind of fill in the blanks as you're going through and putting them in your notebooks, because it's good if you have the examples written out. When we do our direct substitution here, we replace x with 0. We get square root of 1 is 1, 1 minus 1 is 0, and then we get 0 on the bottom. So that's our indeterminate form again. So now we want to use a simplifying technique. So we can't factor because this is not a polynomial, but because when you see a radical, we can rationalize the numerator in this case, because we can move the radical from the top to the bottom if we'd like. That's not something we always do, but it's just another way of rewriting the function. So in order to rationalize, right, basically to turn this into a rational function and move the radical to the bottom, we have to multiply by the conjugate. So if we've got the square root of x plus 1 minus 1, the conjugate of that would be square root of x plus 1 plus 1. So we want to multiply the top by that, and we also have to multiply the bottom because we can't change the original expression. All right, so this is the limit that we're starting with. All right, and now we're going to multiply the top and bottom by the conjugate. All right, and the reason why we do conjugates is because when you have a binomial, a minus b, and you multiply by its conjugate, a plus b, right, you only have to multiply the firsts and the lasts. You don't actually have to FOIL out the whole thing because the outside product and the inside product will always cancel each other out when you have conjugates. All right. So it's kind of like our difference of squares factoring. When you've got a squared minus b squared, it factors into a minus b times a plus b. All right. So really we're just doing our a squared minus our b squared. So we multiply our first two terms together. That gives us just x plus 1. And we multiply our two last terms together, we get minus 1. And on the bottom, we're just going to keep it in factored form. All right. We're going to keep the x factored out. All right. But on the top, so the radical goes away. All right. We get x plus 1. And then we multiply the two last terms, and we get minus 1. And then the radical moves to the bottom. So now what we want to do is try to simplify. So the numerator, we can combine like terms. All right, the 1 minus 1 will cancel each other out. We'll be left with just x on top. And x on the bottom is still factored out. So now we can reduce common factors like we did in the last one. Now that we have a single x on top and on the bottom, we can cancel common factors. And that will lead us to 1 over the square root of x plus 1 plus 1. And now we can do our direct substitution again. The second we cancel these x's, that's going to get rid of our 0 over 0 issue that we were having in the beginning. Right. So now we're going to replace x with 0 in our new function, and we get 1/2 again. It's just coincidence that we got the same answer as the last, or as the first one we did. So what does that mean about our original function? The limit exists at 0, even though the original function doesn't. So there is a removable discontinuity at x equals 0. And if we wanted to, we could go and type this under y1 in our graphing calculator, set up a table around 0, and see that as we approach 0 from the left and right, the y values or the function values should be getting closer and closer to 1/2. Okay, so that was an example of rationalizing. And rationalizing can happen whether the radical was on the top or the bottom. All right, so if it's on the top, you can move it to the bottom like we did here, or if it's on the bottom, you can move it to the top, just so that you can simplify the function like we did here, being able to cancel out those x's. Okay, so the next example is the one with complex fractions. So here we've got the limit as x goes to 2 of 1 over x plus 2 minus 1/4 all over x minus 2. So if we start with our direct substitution, we could plug 2 in. We get 1/4 minus 1/4, which gives us 0. Plug 2 in here. 2 minus 2 is 0. So again, we're getting that 0 over 0, which is our indeterminate form. You always have to start with this first step. So we want to try to find a way of simplifying this. Well, since it's a complex fraction, right, we learned how to simplify complex fractions when we were doing the rational function unit. So we want to multiply the top and bottom by the LCD of the smaller fractions. So the smaller fractions are the ones that are within the big one. So here's our big fraction. So these two are smaller fractions. So the LCD would just be the product of both, which is 4 times x plus 2. All right, so here's our original limit that we started with, and we're going to multiply the top and bottom by the LCD, which would be 4 times the quantity x plus 2. Make sure you put the parentheses in. So on the top, we have to distribute the 4 times x plus 2 to both terms on top. And on the bottom, we're just going to keep everything in factored form. So here, when we multiply the 4 times x plus 2 times the first term, the x plus 2 will cancel with this x plus 2, and we're going to be left with just 4. Minus, when we multiply the 4 times the 1/4 and the x plus 2, the 4s will cancel, and we'll be left with the x plus 2. And on the bottom, we're just going to keep everything in factored form. All right, so we get the 4 from our first term minus the quantity, so make sure you put parentheses, x plus 2. And on the bottom, we're just multiplying the 4 times x minus 2 times x plus 2. The order of them is really irrelevant. So now we can't cancel anything because the top is not factored. So if you wanted to try to cancel out these x plus 2s, you're not allowed to do that because we have subtraction here. We have to be in factored form. So what we're going to do is we're going to distribute the negative, combine like terms on top. That will give us 4 minus 2, which gives us 2, and we have the negative x on top. And the bottom, we're just going to keep it in factored form. We still can't cancel because we don't have any common factors on the top and the bottom. But if we factor out a negative from the top, we get x minus 2 as one of our factors, and now we have a common factor on the top and the bottom. All right, so the x minus 2s can now cancel. All right, so we couldn't cancel up here because we had subtraction, but now since these are being multiplied, there's no number out in front here, we're allowed to cancel the x minus 2s. And once you cancel, that's when you want to do your direct substitution again, because that gets rid of the 0 over 0 issue that we were having. So now we're going to replace all of our x's with 2. And on the bottom, we've got 2 plus 2 is 4. And for some reason, make sure you multiply. I've seen a lot of mistakes made in this unit where everybody puts negative 1/8 as the answer, but it's 4 times 4. So the final answer is negative 1 over 16. All right, so you can find the decimal value for that. And then if you wanted to check this on the graphing calculator, check to see that we are approaching negative 1/16 as x approaches 2 from the left and right. All right, so again, this function would have a removable discontinuity at x equals 2. It would actually have a non-removable discontinuity at x equals negative 2. All right, because when you plug negative 2 in, we get 1 over 0, which again, that's not indeterminate, that's undefined. Now let's take a look at a special case. So this is going to be an example that we can't really do algebraically, but it's one of our special limits. Once we get into calculus, we'll be able to prove it using L'Hopital's rule, but for now, we're just going to trust that we know the limit. So this is one of our special limits. It's a special trig limit, and we can use it to evaluate others as well. If you tried to do direct substitution, sine of 0 is 0, 0 is 0 over 0 on the top and the bottom. But we can't use any of our simplifying techniques for this one. So I just got this answer by doing it on the graphing calculator. So I graphed sine of x over x, set up my table, looked at the values around 0, and saw that this limit equaled 1. All right, so this is just going to be one special one that we have to memorize. But it actually works for a lot of other functions. As long as these two functions are the same, all right, so in this case, they're both x, but they could both be 7x or 3x or 1/2 x. As long as these two functions are the same, this limit will always equal 1. All right, so just kind of showing you here. All right. And the reason I didn't put it, because the variable isn't always x. All right, but as long as these two functions are the same, the limit will be 1. So let's see how we could use this to evaluate some other special limits. So for this one, if we were doing the limit as x goes to 0 of sine of 5x over x, we're going to get 0 over 0, all right, which are indeterminate form. But what we want to do is be able to use the rule that we just stated. So in order for us to evaluate this limit, since the 5x is inside, we need to have a 5x on the bottom. This function here is untouchable. We can't change it. But this one on the bottom, we could change if we wanted to use one of our algebraic techniques. So in order to get a 5x on the bottom, we'd have to multiply the bottom by 5, which we're allowed to do as long as we multiply the top by 5 as well. So we're going to take this original limit that we have. We're going to multiply the top and bottom by 5, all right, which we're allowed to do. So this 5 would have to go out in front. But now we've got the sine of 5x over 5x. So if we look at just this portion, since x is going to 0, right, this 5 is just a coefficient. So if we wanted to, we could actually move it out in front of the limit. All right. And the limit as x goes to 0 of sine of 5x over 5x equals 1. This 5 just stays, or we could, again, think of it as being up front. So our final limit would be 5. All right, so let's look at one more example like that, and then I'll give you the assignment. So now this one's a little trickier because it's not as clear. All right, what we could write it as. And keep in mind, this would actually also work if this had been reciprocated. If we had 2x over sine of 3x, or our original rule, if we had heart over sine heart, as x goes to 0, that limit would also equal 1. So you might see somewhere that's flipped, but the same rule would work. But the key thing here is to look at this function inside. So this 3x can't be changed. All right. So the goal is we want to get the 3x on the bottom. All right. So when we're typing it in, we get our 0 over 0. So the only way we're going to get our 3x on the bottom is to multiply the bottom by 3/2. The 2 will cancel. That will give us the 3. And that also means we need to multiply the top by 3/2 as well. That will give us this limit, sine of 3x over 3x. That limit we've already talked about would equal 1. So the 3/2 stays, and our final answer would be 3/2.